Hi. Now if you have a discrete random variable x, which either follows a binomial model with parameters np, or it follows a Poisson model with parameter lambda, the mean, then under certain conditions for a binomial where n times p is greater than 5 and n times q is greater than 5, q being probability of failure, 1 minus p, or for a Poisson where the mean lambda is greater than 20, then if these conditions are true and we were to plot the probabilities associated with various values, we would find that we would get a distribution that was shaped something like this. If I was to put a curve around it, it would look something like this. And this particular curve is a normal curve. These distributions tend towards the normal curve. So we can say then the random variable x is distributed normally with a mean mu and variance sigma squared, but it's never going to be a normal distribution because we've got discrete random variables going towards a continuous random variable. What I'm saying is that it can be approximated to this distribution. So we'll just say that it follows this distribution approximately. Okay? Now suppose I let these observations here be, say, for instance, these values 27, 28, 29, 30, 31, 32 and 33. It doesn't matter what they are, I just pick this selection of numbers just to demonstrate the next point that I want to make. And that is, we're going to be called upon to work out various probabilities. Maybe, for instance, the probability of being greater than 29 or less than 31 or greater than or equal to 33 and so on. And what we can do is use the approximation to the normal distribution to do this. But we've got to be careful because when we work out these probabilities for the normal distribution, this is going to be given by the area trapped within various regions. And what we've got here is discrete values given by these black lines here. We've got spaces within these intervals. So to get around this problem, what we do is that we imagine boxes of unit width, okay, surrounding these discrete values. So for instance, if I took this value 29 and we had a width of 1 unit here, this would be 28.5 and this would be 29.5 and so on. Now when it comes to working out a probability, let's just for instance say we look at the probability of x being less than, say, 32 for maybe a binomial or a Poisson distribution. It doesn't really matter. But let's say then we've got to work out the probability that x is less than 32. Now if we're approximating it to the normal, then what we do is imagine this. Let's just draw a little diagram here. Okay, we're looking at this section here where this represents the 32 and we've got the graph coming down through the 32, something like this. Okay, now if we've got to work out the probability of x being less than 32 as an approximation to this normal distribution, then that is represented to the area to the left of 32. Now we've got to be very careful here because can you see that what we've got here is a little bit of this block that sticks out over the curve. But then on the other hand, we've got a section here which seems to miss part of that block. So what we do is apply something called a continuity correction to adjust for this kind of loss of area, if you like. So we're trying to find the probability that x is less than 32. We want the area to the left of 32, but it mustn't include 32 because it's got to be less than 32. So what we do is we concentrate on this area just to the left of 32, but not including it, so we don't go into the box here. So this value here, okay, which is this one here, is at 31.5. This one here would have been at 32.5, but we're only interested in 31.5. So what we can say is that this probability is approximately the same then as working out the probability that x is less than 31.5. And this is, as I say, is called a continuity correction. Continuity corrections are used then when approximating a discrete random variable to a continuous random variable. And what we would then go on to do is use this value with the normal distribution to work out an approximate value to this one. And I'll be doing that in further tutorials, but we'll be needing the continuity correction. So hopefully this gives you a guide. Now it doesn't just stop here, okay, because you could be asked, for instance, to work out the probability that your random variable x is less than or equal to a given value. Let's suppose we take 29. It doesn't matter what side this is on, okay, it could be on this side, the same principle would hold. And that is, if we just consider this box here, okay, round 29. So if we just go to that box, this is the value 29, and the curve in another example could be coming down. In this example it's going up, but it doesn't change the situation at all, because we want to be less than or equal to 29, so we need to be to the left of the 29. But because it says less than or equal to 29, that area now has to include the 29. So we go into the box and we go right past the 29 out to the other side. And the other side here is the value 29.5, whereas this one here was 28.5. So with the continuity correction, this is the same as working out the probability that x is less than 29.5. Notice we don't put an equals here, okay, when we're dealing with a continuous random variable. So it's same as working out that x is less than 29.5. Okay, now that is, again, isn't the only things that we can have, because